Welcome back to Logical Thinking, and before we talk about the different forms of deductive arguments, I'm going to talk about DeMorgan's laws, which are named after the 19th century British mathematician and logician Augustus De Morgan. These rules can help make certain proofs easier, and they're also used in circuit theory to help make things more efficient, cheaper, and faster. Now, before we get started, let me give you a quick definition. Two propositions are said to be logically equivalent if they have the same truth value in every model. And one easy way we can show two propositions are logically equivalent is to basically show that they have the same truth table, which means writing out the truth table and then just showing how each propositions have the same truth value. And often what we'll do is we'll use this triple equal sign to denote logical equivalence. And note here we're not using the normal equal sign with two lines. And this is because we haven't defined what equals means in terms of propositions, at least not formally. Logical equivalence is simply saying that two propositions have the same truth value, not that the two propositions refer to the same exact thing. For a simple example, if we look here at double negation, if we can show that the truth table for P is equal to the truth table for not P, we'll show that P and its double negation are logically equivalent. So let's go ahead and write P, and not P. Now P only has two possible values, true or false, so we'll write those down. And let's look at this second column. When P is true, not P is false. And when P is false, not P is true. So once again, we're just flipping the values, pretty straightforward. And moving on to that next column, we can basically treat not P as the negation of not P. So what we can do is just flip the value of not P. So when not P is false, not P is true. And when not P is true, we're going to put a false there. Not P is false. And looking at these two rows in the truth table, when P is true, not P is true, and when P is false, not P is false, showing that the two are logically equivalent. The nice thing about this is this shows that we can always replace the double negative of a proposition with the original proposition whenever we need to. And since P was arbitrary, we can use this double negation property of compound propositions as well. So for instance, remember we can chain these together. So P could itself be a proposition that's made out of, say, the conjunction of A and B. We'll be using this idea of equivalent truth tables to show that De Morgan's laws work. To motivate De Morgan's laws, remember that A and B is true only when A and B are both true and it's false otherwise. So another way to say this is if A and B is false, at least one of them, A or B, has to be false. And likewise, if A or B is false, then A and B both have to be false because A or B is true if one of them is true. Now, as an aside, remember from our truth schema assumption that saying not A is the same as saying A is false. And we can write the idea behind De Morgan's laws as follows. Not quantity A and B is logically equivalent to not A or not B. Once again, if A and B is false, this is the same thing as saying not A and B, then at least A or B has to be false because otherwise A and B would be true if they're both true. There's only one case in which they're true. So let's go ahead and construct the truth table here. On the right, I'm going to put not quantity A and B, and we're going to have not A or not B, which is eventually where we're going to try to get to show that they're equivalent. But let's go ahead and first put A and B on the table. Now we're going to need 4 rows here, 2 by 2, to cover each of the possible values of A and B. So let's put A and B here on our truth table and make sure we cover all 4 cases. Now what we're going to do is I'm going to put not A and not B here on the table because we're going to need these later for the right-hand side. So for not A, once again, we're going to take our values of A and simply flop them like so. When A is true, not A is false, and when A is false, not A is true. And likewise with not B, we're going to take B and we're going to flip it. So when B is true, not B is false. And when B is false, not B is true. Now let's look at A and B. And remember that A and B is true if and only if A and B are both true and it's false otherwise. So looking at these values here, we're going to put true because they're both true in that first row. And all of the other ones have at least one value of false that we're going to have here. Now, moving on to not quantity A and B, we're going to just take our value of A and B and simply negate it. So when A and B is true, we're going to put false here in the truth table. And when A and B is false, we're going to put true. Now we need to get the truth table for this right-hand side. This is not A or not B. So let's look at not A or not B. We already have them in the table. And remember that for two propositions P and Q, P or Q is true if either of them or both are true, and it's false otherwise. So it's false here in this first row because both of the arguments are false, and these next ones are going to be true. And from here, we've actually completed the truth table for not quantity A and B and not A or not B. And if you look at each row, all of these four rows, they have the same value. So what we've done is we've shown that not quantity A and B is logically equivalent to not A or not B. Now, what about the other side? This works in the other direction as well. We showed the opposite. We showed that not quantity A and B is equivalent to not A or not B, but we can actually look at this the other way as well. We can say not quantity A or B is logically equivalent to not A and not B. And the reason for this is, and I'm not going to do the truth table, although if you're not sure about it, you should convince yourself that this is the case, but it does help to just look at the truth table for the disjunction. If we put A and B here and we consider all of our possible values, A or B, or A disjunction B, is true in all cases except when both of them are false. So this is like saying for A or B to be false, A and B both have to be false individually. That's the only way that we can get false from it. So that's one of the ways we can say it. We can say A or B is false if and only if both A and B are false, or not A and not B. So looking here at that last line in the table, that's the one we're trying to capture here. And another way we can write this is saying not quantity A or B if and only if not A and not B. And using our symbol for the disjunction that we talked about in our video on logical connectives, we can write this double-sided arrow, which once again also tells us about logical equivalence. So this tells us a few things that are kind of interesting if you reflect on this. The first thing to note is that negation does not distribute across parentheses when you have conjunctions and disjunctions. And one way to remember this is like saying in algebra, quantity A plus B squared is not equal to A squared plus B squared. When you distribute negation, you need to be sure to flip-flop your ands and ors. And remember the logic here. You can extend this to more cases by just kind of thinking about it. You can also write a truth table, but just kind of thinking about what's required for the left-hand side to equal the right-hand side. So one of the ways you can think about this is to say, if A or B or C, which is what we have here, is false, then all of the parts, A and B and C, all those propositions, have to be false, because if at least one of them is true, then the disjunction of all of them is going to be true. And likewise, if the conjunction of them is false, at least one of them has to be false, because if they were all true, then the conjunction of all of them would be true. So this is just kind of a fancy way of capturing this idea. Similarly, you can negate DeMorgan's laws using the double negation property that we showed at the start of this video to get values to the form A and B. So basically what we do is we take DeMorgan's laws, we negate both sides, and we can have that A and B is logically equivalent to not quantity, not A or B. And likewise, A or B is logically equivalent to not quantity, not A and not B. When you're looking at these compound conjunctions like we see here with A or B or C, one of the things that can be helpful is to consider the conjunction as a conjunction of more broken down propositions. So you can consider this as not quantity A or, so A's disjunction with B and C as its own proposition, which of course B and C as a proposition, you can assign that to some variable, say P, is itself a conjunction of B and C. And you can kind of build it up that way. That's one way you can build these up to be longer. But in general, once again, you can kind of generalize this to a general rule by saying when you distribute negation, you're going to have to flip your conjunctions and disjunctions. Lastly, when it comes to circuits, we can actually use fewer pieces and fewer circuit components using DeMorgan's laws. On the right-hand side, you actually have three gates. You have two inverters, which you see A and B going into these inverters. Remember that those bubbles mean inversion. And then you have an AND or an OR. Versus on the left-hand side, you actually have only two gates. You have an OR or an AND with an inverter at the end. And actually, you can build NORs and NANDs directly out of transistors without even needing to do a negation by being clever with your transistors. But if not, once again, this is a helpful way of just thinking about the logic, but I think the intuition here is more important. So once again, this can help us save parts and money, but just remember the fact that if the conjunction of several statements is false, at least one of them has to be false. And if the disjunction of all of them is false, then all of them have to be false. Thanks for watching, and in the next video, we'll talk about the 3 laws of thought. And in future videos, you'll see how we can use DeMorgan's laws to help us with proofs in mathematics.